All right, so we've already talked about an introduction to vector valued functions and how to deal with them and how they're created. This is part 2 of those notes, and we're going to start with dealing with limits. So when you have a vector valued function, we've talked about how to evaluate it, but what if you can't evaluate it? What if you just want to know where it's going, if you want to know its behavior around a certain value of t? Well, that's where limits come in. So since vector valued functions are always in terms of t, when I take the limit, I just need the limit as t approaches one value. So I only need one value for approaching. And really everything else that I'm about to talk about is stuff you already know for limits, except instead of evaluating a limit once, you evaluate a limit 3 separate times. So if we look at number 6 here, number 6 says the limit as t approaches 2 of ti, t squared minus 4 over t squared minus 2t, and 1 over t. All we do is think about these as 3 independent functions, or expressions I should say, and then evaluate those as t approaches 2. So if I take the limit as t approaches 2 of t, I'm just going to get 2. And if I take the limit as t approaches 2 of t squared minus 4 over t squared minus 2t, this I'm going to evaluate after simplifying. So t squared minus 4 is t plus 2, t minus 2. And this is t times t minus 2. It's like begging to be simplified. I can cancel out the t minus 2's, and I have t plus 2 over t. Now I can evaluate that simplified form, and I end up with 4 over 2, which is another 2. Okay, cool. And then if I take the limit as t approaches 2 of 1 over t, I get a half. So 2, 2, a half means the limit of the vector valued function is the vector 2, 2, a half. And that's it. From here on out, we're just going to use the limit laws that you've used before to figure out what the limit equals. So then if we come down here, we're just going to do the same thing. So if we take the limit as t approaches 0 of e to the t, that's going to be 1. The limit as t approaches 0 of sine t over t. That's one that you should have memorized from, oh, I don't know, let's see, probably a year ago for most of you. But if you don't remember that, one of the other things you might remember is the L'Hopital's rule. If you take the limit as t approaches 0, this goes to 0 over 0, which means that this limit has the same value as the limit you can evaluate where you take the derivative of the top and the derivative of the bottom. So L'Hopital's rule says if you get 0 over 0 or infinity over infinity, you can take the derivative of the top and the bottom and individually, and then take the limit again. So the limit as t approaches 0 now is cosine 0, which is 1, over 1, which is another 1. And then the limit as t approaches 0 of e to the negative t is yet another 1. So this guy right here has a value of 1, 1, 1. If I take the limit as t approaches 0 of this last guy here, tell you what, I'm going to do it, but I'm going to do it quietly, so I'm just going to write it on here. Watch and go along as you can, or you can be writing it down right now and then check with my answer, okay? So if you followed along, the first and the last were easy. You just plug in 0, and the second one you have to use L'Hopital's rule because you get a 0 over 0. That's not really simplifiable. So we do L'Hopital's rule there and get, if I'm not mistaken, 2. So our limit is 1, 2, 0. And that's it. That's limits. Other things you can do with multivariable functions is when you graph them, you can see where they intersect. That's kind of cool, right? So I've got a cylinder here and a plane, and I want to know what's going to happen when these two things intersect, okay? So if you want to find a vector valued function that will represent the curve of intersection of a surface and an object, we write the parametric equations for x, y, and z in terms of t. That's called the parameterization of the curve, and that'll map the intersection of the surface and the object. So find a vector value function that represents the curve of intersection of the cylinder, this, and the plane, that, using the parameter x equals cosine t. So all we need to do here is kind of make a domino effect with our givens. So x equals cosine t. So if x equals cosine t and x squared plus y squared has to equal 1, I would have cosine t squared, or cosine squared t, plus y squared needs to equal 1. Well, cos squared plus what squared equals 1? There's an identity that says cos squared plus sine squared equals 1, so we can then say y equals sine squared t. And you might be thinking, wait, what just happened? That kind of came out of left field. Well, these all do. Your parameterizations, there are an infinite number of parameterizations for any curve. Some are obviously more eloquent than others, but really you can parameterize things in a lot of different ways. I'm trying to give you the most eloquent, efficient way. So if x equals cosine t, what could y be so that this has to equal 1? Well, y could be sine t. So y squared equals sine squared t. So I should probably change that a little bit. So y is sine t. And then I have an x, I have a y. Now I need a z component for my parameterization. So y plus z is supposed to equal 2. And y is sine t. So z is 2 minus sine t. So the parameterization of this ellipse right here would be the set of parametric equations x equals cos t, y equals sine t, and z equals 2 minus sine t. And that's the parameterization of the intersections. So we'll do one more. Find a vector valued function to represent the intersection of this semi-ellipsoid and the parabolic cylinder y equals x squared. So basically, imagine like you have a ball like this, and we take a piece of paper and I make like a U shape out of it like this. So imagine this is like a piece of paper and I've bent it into a U shape, and I bend it down and slice right through the ball. It's going to trace out this cut line on the ball. So we're trying to figure out what's the equation of that curvy line right there. So we're going to do the same thing. We're going to do parameterization. So we have x equals t, and since y equals x squared and x equals t, y equals t squared. And since x squared over 12 plus y squared over 24 plus z squared over 4 equals 1, I can say, well, t squared over 12 plus t to the 4th, because again, y is t squared, t to the 4th over 24 plus z squared over 4 equals 1. And then I can just solve for z. Multiply everybody by 4, and I get z squared equals 4 minus t squared over, t squared, there we go, over 3, minus t to the 4th over 6, if I multiply both sides by 4, and then square root it. Now, technically when you square root something, you need the plus or the minus, but I'm only dealing with this portion, which has positive z values, so I just need the positive square root. And there it is. Alrighty? That, my friends, is that. We are done with parameterizations. And we have finished our notes on 12.1, basically an intro to vector valued functions. All right, and I got to end with a joke. The joke today is going to be, what do you get when you cross a snowball with a vampire? Frostbite. I know that one's really bad. It's like a 3-year-old joke, but hey, it's wintry out. All right, talk with you again soon.